So you've seen that at equilibrium, there's an equilibrium expression that involves an equilibrium constant. That was originally noted empirically by doing experiments. It was found that that expression held for any reaction. We can understand why it holds from a variety of different perspectives. Let's look at one that involves kinetics, since we've talked about kinetics. So this equilibrium constant expression, sometimes called the law of mass action, is something that has been shown to hold in the condition where each and every step in the underlying kinetic mechanism is at equilibrium. So the reaction is still proceeding forward and backwards, but all of the rates are balanced. And this is why we often refer to this as a dynamic equilibrium. The idea is that for each step in the mechanism, the forward rate is equal to the reverse rate. This is sometimes called detailed balance. The principle of detailed balance says that these rates are equal, and there's another fancy term, microscopic reversibility, which says that on a microscopic scale, all of these different steps can go in the forward and backward directions, and in fact are doing that at all times. So let's look at a couple of examples to illustrate this. The first one we'll look at is a simple one-step mechanism. And as an example, we'll choose the classic reaction that everybody talks about in general chemistry courses, which is the dissociation of N2O4 to make NO2 molecules. So there's a rate constant for going in the forward direction, K1, and there's a rate constant for going in the reverse direction, which we'll call K to the minus 1. As we just said, at equilibrium, what we're saying is that the rate of the forward direction, forward rate, has to be the same as the reverse rate. And for individual steps in a mechanism, individual elementary steps, we know how to write those rates in terms of the rate constant and the concentrations of the reacting species. I'm going to put a little equilibrium down here because this is going to hold at equilibrium. If you're not at equilibrium, one or the other of these rates can be faster than the other. So this has to be equal to K to the minus 1 times the rate in the opposite direction. And we know that because there's two NO2 molecules coming together in that direction, we have to square the concentration. So what does this give us? We just wrote that the forward rate is equal to the reverse rate. Let's solve that for the concentration of NO2 squared at equilibrium divided by the concentration of N2O4 at equilibrium. And if you look at this expression, that's just equal to the ratio of the forward and reverse rate constants. And you'll recognize that this expression, this so-called law of mass action, is equal to the equilibrium constant, big K, for the reaction. So equilibrium constants are capital Ks, rate constants are small k's. So what this shows us then is that the equilibrium constant is really, in terms of a mechanism, nothing other than a ratio of rate constants. These rate constants are independent of concentration, so big K is also independent of concentration. The rate constants depend on temperature, so big K also depends on temperature. Let's look at one more example, this time for a multi-step reaction. And I'm going to create my own little alphabet soup reaction here where we have two atoms of B, whatever B is, that come together with a forward and reverse rate constant to form an intermediate, B2. B2 then reacts after colliding with molecule or atom A in a second step that has a forward and reverse rate constant, K2 and K to the minus 2, to make the product AB2. So the overall reaction then, if I cancel out the intermediate B2, is A plus 2B goes to make A B2. In order to analyze this under the condition of equilibrium, we're going to do exactly the same thing that we did for the one-step mechanism previously. We're going to write the forward rate for each of these steps as being equal to the reverse rate. That's going to give us two expressions here that we can combine to see how they relate to the equilibrium expression. So in this case, I'm going to say the forward rate is K1 times B squared. That comes from understanding how to write the rates for these elementary steps. That has to be equal to the rate in the reverse direction, K to the minus 1 times B2. We can do the same thing for the second step using the stoichiometry of that step. We see that the forward rate is K2 times A times B2. That's equal to the reverse rate constant, K to the minus 2 times A B2. So I now have two expressions. At equilibrium, we're saying each of these is equal to each other. And so I can look at a ratio of products over reactants for both of these steps. So let's go ahead and do that. From these equilibrium expressions where we equated forward and reverse rates, we've seen that we can now solve for various ratios of concentrations of species in this mechanism. So for example, from the first step, you find that there's a equilibrium-like expression with an equilibrium constant K1. That's the ratio of the forward and reverse rate constants. Likewise, for the second step, we can write an analogous expression that involves concentrations of products over concentrations of reactants in that step. And this one is now related to the ratio of the forward and reverse rate constants for the second step. If I combine these together, we know that overall, the equilibrium expression that we've seen previously has to be related to the product for the overall reaction divided by the reactants in the overall reaction, the concentrations raised to their stoichiometric powers. And if you look at these expressions up here, what you'll see is that that's equal to the product of these two things, which is K1 times K2. And so in this case, we see that the overall equilibrium constant is now, again, a ratio of forward and reverse rate constants, but now there are multiple pieces in here that come from the multiple steps on the reaction. So again, there's the equilibrium constant on one side, independent of concentration, dependent on temperature, and on this side we have rate constants for the steps in the mechanism that are also independent of concentration but dependent on temperature. I've done one specific example here, but this is a very general result. Any mechanism whose individual steps add up to the overall rate constant will give you this result, and any good mechanism has to do that. So even if we don't know the actual underlying mechanism, this result will hold. So this explains why it is that from a kinetic point of view, this equilibrium expression, the equilibrium constant equal to concentrations of products over concentrations of reactants to their powers, why that holds, and why it's independent of these equilibrium concentrations.